Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Abutiwa Sos Ugobela Wemets. And without any further ado, let's look at these questions that we have here. Okay, so we have question 8 on electrodynamics. It says the diagram below shows a type of generator and the coil rotates clockwise. So we can see that we are given the direction of the rotation of the coil. Then 8.1 says, name this type of generator. Is it AC or DC? Now, in order to determine that, you only have to check whether it is a split ring commutator or it's a slip ring. Now, from this, we can tell that this is obviously a split ring commutator, so this makes it DC. So 8.2 is also saying give a reason for your answer. So let's just answer 8.1 and 8.2 all together. So we say it's a DC because it is a split ring commutator. Then 8.3 says for the position of the coil is shown, in which direction will the current flow? Simply state A to B or B to A. Now, what we know is that the rotation of the coil in a generator is same as the rotation of the flow, or is the same as the direction of the flow of the current. So that means if this coil is rotating clockwise, also your current needs to flow in a clockwise direction. Now if it flows in a clockwise direction, that means it will be going all the way from A to B, right? So for 8.3, we are going to say A to B, because in a generator, the direction of the rotation of coil is the same as the direction of flow of current. But then note that this only happens for a generator. For a motor, it is opposite. If the direction of rotation of the coil is clockwise, then the current would flow anti-clockwise, right? So note that for the motor, it's different. And then for the generator, it's always in the same direction. So this is an easier way to remember that, other than just having to do that stupid thing with the left hand and the right hand. Okay, so moving to 8.5, it says if the voltmeter shows a maximum voltage output of 8 volts across the 5 ohm resistor, meant to say, calculate the RMS current output of the generator. Right, so I will give you two methods into solving this. The first one, you can approach it like this. So you have your 8.5 here. We are trying to calculate the RMS current. We are given the maximum voltage, which is your Vmax, and then we are also given the resistance. Now you can try to calculate the Vrms using the Vmax. So that would be Vmax over root 2, and then you simply just take your Vmax, which is 8, and then divide it by root 2, right? And then this, when you punch it in your calculator, it's supposed to give you 4 root 2. Then that's your Vrms. So I'm not going to write it in terms of decimals because I don't want to round off as yet. Remember, it's not the final answer. Then, in order to now calculate the IRMS current, I will go IRMS is equals to Vrms over R. So this formula here has been taken from R is equals to V over I. So I've just made I the subject of the formula, then it becomes Vrms over R. Then my Vrms is 4 root 2, and then my resistance I've been given, it's 5. Now you can punch this into your calculator and round off to 2 decimal places. This is going to be 1.13 amperes, right? So this is one option of doing it. So option number 1. Option number 2, you can choose to just calculate the Imax from the Vmax here. So now that you are given the Vmax, you can say, let me calculate the Imax. And then you'll have Vmax over R, also taken from this. So my Vmax is 8, then divide that by 5. I will get 1.6 amperes. Right, so let me note here it's V. And then to calculate now the IRMS, now that I have the Imax, I'm just going to use the formula Imax over root 2. Then it's 1.6 divided by root 2, which if you punch it into your calculator, you still get 1.13 amperes, right? So either way, you could have landed to the correct answer. Your choice in the way you approach it, right? Okay, then now let's look at 8.6. It says starting with the coil in the horizontal position. Note that. Now there's a catch there, right? In most of the times, even when you do it in class, you normally see this coil in a vertical position, right? So normally in a vertical position, that's the starting point, right? So that's where your magnetic field or your magnetic flux is just zero. But then now when it's at a horizontal position, this is at the point where it exhibits a maximum magnetic flux, right? So now they want you to draw it starting from that horizontal position. There is one thing that I want you to note in this, right? So I will draw it in the vertical position and also in the horizontal position so that you know the difference. Then 8.6.1 says draw a sketch graph of the output voltage for one cycle of the coil. Let's start with the one that you are used to, the standard one. So which is you find it in a vertical position. Right, so this is when your coil is something like this. I'm not good in drawing, but then you get something like that, right? So this is when it's in a vertical position. Now, that is, you will have tar, and then it's DC, right? So for DC, you just have two bounces there, like that. Not the nicest, but then you get the whole idea. So this one must be in equal length, right? So this is what you have. So obviously you'd indicate that your maximum here is 8 volts, right? So you'd indicate that it's 8 volt because we are given the output. So yes. Then, okay, cool. This is the one in vertical position. Now, let's draw the one that they're looking for in horizontal position. So note that if it's starting in a vertical position, at that point, because there's no magnetic flux linkage in the coil, that means the EMF involved has to be zero. So it's starting where EMF is zero. But then if you have to draw the one for the horizontal position, at that point, we are saying that the EMF is at its highest, right? So that means it has to start there. But then because it needs to complete one full cycle, remember, this is half a cycle, and a half a cycle, that's a full cycle. But this is a quarter of a cycle, and then this is half of a cycle. Then we need another quarter so that it makes half with this. And then now we have a full cycle, right? So all of this should be in the same length. And then we have our 8 volts. And then this is EMF in volts. And then down here we have time in seconds. So time in seconds. So this is the difference between the two. If they say draw the one in vertical position, this is how it should be. But then if they say draw in horizontal position, note that it starts from the maximum and then goes down and then bounces up to the maximum, goes down and then bounces up back to the maximum. Right. So just to note that different. It is very important. Okay, then 8.6.2 says, will the generator output current graph differ from the output voltage graph? Simply state yes or no, right? And then 8.6.3 saying, explain your answer to question 8.6.2. So let's just try to answer all these two together. So now, will the shape be different if we were to draw the output current graph? Definitely not, right? And then we say that because we say no, because the induced EMF drives current through the conductors such that the EMF and current are in phase, right? So if they're in phase, that means they will also have the same shape of graphs. So the induced EMF drives current through the conductors such that the EMF and current are in phase. Therefore, the shape of the graph is the same, right? So that's how you were supposed to go about tackling that question for a maximum of 15 marks. Okay, so we have question 9. It says the diagram below shows the essential parts of a generator, right? So again, this is a generator here. And then 9.1 says, is this an AC or DC generator? Give a reason for the answer, right? And then We already know this is AC because it has slip rings. So this here, as weirdly as they've been drawn, these are slip rings. Then 9.2 says the coil ABCD rotates clockwise within the magnetic field. Draw the shape of the voltage established across the external resistor for 2 cycles of the coil. For what? 2 cycles of the coil. Start with the coil in a horizontal position as shown. Now again, this must be drawn in a horizontal position. So in the previous video, I showed you that you need to be careful if they say horizontal position, because most of the time we are used to drawing the one that is in vertical position. But this time around, they want you to start at the horizontal position whereby it has the maximum EMF, right? So the way you draw that one, let me take you through that. So let me again first start by drawing the one that you are used to, which is in vertical position, this one. So the one in vertical position, because it's AC, the 2 cycles would look like this. Remember, this is 1 cycle. I need to take art classes because, wow. Then this is 1 cycle. And then this is another cycle. So normally this is the graph that you would have for an AC if this was in vertical position. So if this was in vertical position, this is the type of shape that you would have, right? But then now, because they want you to start drawing it from the horizontal position, you have to note that it will not start at 0. It will now start at the maximum voltage, right? So it's supposed to go like this. Okay. So this here indicating 1 full cycle. So we can see quarter, quarter and half. Then that makes it a full cycle. So because we have to draw 2, then I have to repeat the same shape again. Then that's it. That's how we have that. Right. So EMF here in voltage, and then down here we will have time in seconds. Right. So that's our EMF versus time graph. And then now we know the difference. Right. So the one that we are supposed to draw is this one here. Okay. Now let's go to 9.3. 9.3 says, with the coil starting in the horizontal position as shown, what would be the direction of the induced current? Choose from A to B or B to A, right? So with this one, again, we know when it comes to a generator, we said that the direction of rotation of the coil is in the same direction as the flow of current. So because our coil is rotating clockwise, we know that our current also has to flow clockwise. So that means our current will be going all the way from C to D, and then D all the way to A, and then from A all the way to B. So that means we will choose A to B. So for 9.3, this is A to B. Right. Then 9.4 says the generator shown above delivers a maximum voltage of 6 volts. And then 9.4.1 says define the term RMS current. So we already know how to define that one. We say it's the AC current that dissipates the same amount of energy as an equivalent DC current. Right. Then, okay, for 9.4.2 now, it says calculate the RMS current of this generator. Right. So to calculate the RMS current, we are given the Vmax here. So maximum voltage. But then the error that they made with this question is that they didn't give you the resistance. But then we later found out that the resistance here was supposed to be 10 ohm according to the memorandum. So let's use the resistance of 10 ohm. And then this is 9.4.2. So to calculate that, we will start by first calculating the VRMS. and then this is V max over root 2. So the V max is 6, and then over root 2, we punch that into our calculator, we get 3 root 2, right? And then to then calculate the IRMS from our equation, R is equals to V over I, we can make I the subject of the formula. This will be VRMS over R. Then we have our 3 root 2 over the resistance of 10. So when we punch that into our calculator, we get 0.424 amperes, right? So just choosing to round it off to 3 decimal places, then that's it. Okay, then to further calculate the average power dissipated at the external load, then this is how I'm going to do it. The formula for power, remember, we have several formulas for power. We have P is equals to I squared IRMS, and then times R. And then we also have PVRMS square over R. And then we have P is equals to IRMS times VRMS, or VRMS times IRMS, it's all the same. Then given the fact that we have all of this, right, we do have the IRMS, we do have the resistance, we can choose any formula that we want to work with, right? So I'm just going to go with the first formula there because I just calculated the RMS current. And then I will say IRMS square times R. So this is supposed to give me, the IRMS is 0.424, and then square that. Then the resistance we said is 10. So when we multiply there, we will get 1.8 watts. So if we just round off, it's just 1.80 watts, right? And then there we go. Okay, so we have question 11. It says a learner built the following simple generator based on a dynamo used to power bicycle headlights. He used the generator to demonstrate that he could use mechanical energy to generate electrical energy, right? And then is this a DC or an AC generator? Give a reason for the answer, right? So remember, you will be turning on the wheel or crank there. So that means this is AC because the magnetic field will be changing continuously, which causes the current through the globe to alternate direction, right? So the magnetic field changes continuously, which causes the current through the globe to alternate direction. Then 11.2 says, how will the learner know that the electrical energy is produced? Now it's obvious, the globe will light up. So when the globe lights up, then it knows that electrical energy is being produced there, right? Then 11.3 says, explain how this generator is able to produce electrical current when there is no electrical connection between the rotating magnet and the copper coil. So the way you'll be explaining this is based on the principle of Faraday's law of electromagnetic induction, whereby we know that according to this formula here, E is equals to negative N change in phi over delta T. We know that the magnetic flux linkage with the copper coil changes continuously, as we said, that this is AC current, then this will cause an induced EMF in the copper coil. Thus, the current is able to flow through the globe because the coil is part of the circuit. So we explain that the magnetic flux linkage induces an EMF in the coil. And since the EMF is induced, that means the current will also be able to flow through the globe because now the coil is part of the circuit, right? Okay, then let's now proceed to the next question. It says, list 2 changes that can be made to the generator to increase the brightness of the globe. Then how can we increase the brightness of the globe? We know that what will lead to us increasing the brightness of the globe is if we increase the induced EMF, which will then increase the current, right? So to achieve that, we must increase the speed of the wheel so we can rotate the wheel or the crank much faster. And then we can increase the number of turns on the coil. So on that coil, we can try to increase the number of turns, and then we can also use a stronger magnet. So if we use a stronger magnet or a bigger magnet, then we are able to induce much of the EMF and therefore produce much current. Right, then a generator or dynamo used to power a light on a bicycle needs an average power of 6 watts and a potential difference of 12 volts, which is VRMS. Then now they say calculate the maximum current that can flow through the globe. Then in order to calculate that, we know that we have to first make use of what we are given here. We are given the power, and then we are also given the VRMS. We are looking for the Imax. So the first thing that we would need to calculate is IRMS. Now we know from the formula, power average is equals to VRMS times IRMS. We can calculate the IRMS here. The power average is 6 watts, and then the VRMS is 12. And then now we are left with this IRMS, then divide by 12 both sides. Our IRMS will be equals to 0.5 amperes. Now to calculate the Imax, we write the formula IRMS is equals to Imax over root 2. Then simply substitute IRMS 0.5 and then Imax over root 2. At this point, we know that we just have to cross multiply here and then find our value for Imax is 0.707 amperes, which if you round off to 2 decimal places, as per the instruction of the exam, that's 0.71 amperes, right? And then that's how you would go about solving this question. So it was all for about 13 marks, not a very hard question. It was just more of conceptual questions there that you need to understand to check if you understand the whole operation of a generator. But then with all that being said, guys, please press the thumbs up button if you've enjoyed the lesson and then you found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.